My name is Yuki Chen, and this is my colleague Li Nanhao. We are from 316, Qihu 316, and we are very glad to be here. Today we are going to give a topic on the advanced exploitation of Internet Explorer. Early this year, we attended the Pontoon contest in Vancouver, and we target Internet Explorer 64-bit, and we finally succeeded in the target. There are some significant rule changes in this year's IE target. For example, this is the first year that 46-bit, 64-bit Internet Explorer is used as the target. This means many exploit techniques such as simple heap spraying will not work in 64-bit Internet Explorer. And also, this year's contest enables the enhanced protect mode in Internet Explorer, which means after we achieved remote code execution in IE, we still need to bypass the sandbox to win this game. And what's more, in the previous year, Microsoft had added many exploit mitigations, such as the isolated heap, the deferred free. And these mitigations are very efficient, and they killed many useful bugs which can be used originally. So, as Wupon CEO Shaoqi Becker said, this year's Pontoon is a joke. Reduced the price, but the difficulty increased very much. By the way, this year's price for IE is 65,000, and last year is 100,000. But this year is much more difficult than last year. But we do not want to wait for next year, so we decided to take this challenge. And fortunately, we finally succeeded in the challenge, and so today we want to give some sharing about the vulnerabilities we used in our exploit, as well as the techniques we used to finally take down the Explorer. So this is our agenda today. Basically, we have two parts. Since we used 2 zero-day vulnerabilities in the contest, so we have two parts. The first part, we will introduce the first 0-day, which is CVE 2015 and 1745. This is an initialized memory bug. We used this bug to achieve remote code execution in the IE sandbox process. And the second part is we will introduce another 0-day we used to bypass the enhanced protected mode of Internet Explorer. And this bug is a race condition bug. It exists in the IE broker service. Who are we? We are researchers from 360 Vulkan team. 360 is the largest internet security company in China, and basically we do security researches, including vulnerability research, APT detection, and security software developing. And we have found some vulnerabilities, and also we attended some mitigation bypass reward Pontoon, and we have spoken in several security conferences. Okay, now let's start our today's topic. The first part, we will introduce the initialized memory bug and how we use this to achieve remote code execution. And Linan will present this part for you.
All right. Hello? Can you hear me? Okay. All right. Let's start with the first part, which is unnaturalized memory bug. We use it to achieve RCE, to achieve remote code execution. And so, what is unnaturalized bug? It is one category of memory corruption bugs. When you write program, you will access to the memory, and if your program use local variable, global variable, or dynamic locate buffers, then your program will accessing to the memory data. So if your program use this memory data, but before initialize it, you may get the unpredictable result. And we call it unnaturalized memory bug. Here we have two examples. The first one, we allocate an int array with 10 elements on the heap, and then we access to the first element of this array, but without initialize it. So this is an unnaturalized memory bug on the heap. And see the second one, we have an int array with 10 elements on the stack this time, and still we access to the first element of this array without initialize it. This time, this is a typical unnaturalized local variable bug. Unnaturalized memory bugs are common in program. You can find many bugs of this kind in history. There are many net bugs. As you can see here, MS Chamel, Flash, also in Windows kernel, all have this kind of bugs. Here you can see the red bag. And if you successfully allocate a memory block, you will own this memory block. And if you access this memory block before initialize it, you will get unpredictable result. Using such unnaturalized memory data is similar to that you get on the tree and take a seed. Suddenly, you find there's a bag there. There's a bag left by the previous passenger maybe, but you cannot directly use this bag because it's not yours. Doing this will lead to bad result. I mean, maybe it is a boom. And this is our bug. We found it by fuzzing, and it is caused by C attribute value in C attribute array. This time, the C attribute value is the red bag. Is that red bag left by the previous passenger? So, what is the C attribute value? You know the DOM element in HTML can have attributes. You can set attribute to a DOM element using JavaScript like this by calling function get attribute. And the C attribute value is an underline data struct that store an attribute. C attribute array, as its name indicates, is an object that can contain an array of many C attribute values. We need to go a little deeper into the C attribute value and the C attribute array for better understanding the exploit process later. C attribute value consists of some flag fields and value fields. A C attribute value actually is a variant date type, which means it can contain various type of date. The second byte in the C attribute value is important because it indicates the type of this attribute. So we call it VT type in red. And if, for example, if the VT type is 8, then this attribute should be a BSTR string attribute. Let's look at an example. Here we create a div element and set an attribute to this element. Let's have a look at the memory date of this C div element in debugger. First, you can see there is a C attribute array stored in the C div element. Then we falling into this C attribute array, and we can get another pointer to an array of many C attribute values. So we dump the first C attribute value. You can see it here, and it is exactly the attribute we just set to the C div element. And the VT type is 8, which means this attribute should be a BSTR attribute. And we see the value type, we see the value field is point to a BSTR3. This is a simplified POC of our bug. We have two elements here. The first one is the ith element in the document, and the second one is the body element. First, we set some attributes to these two elements. Then we call the function merge attribute to them. The function merge attribute will merge all the attributes of these two elements to a new created C attribute array. And so the body element will contain the new created C attribute array after this call. And the bug exists in the implementation of this function. I mean the function merge attribute. As you can see here, during the merge, the first node in the new created C attribute array is just skipped without being initialized. So it gave us an initialized C attribute value, which can be accessed in JavaScript. To exploit this bug, we have several steps. First, since we cannot directly use the heap spree in 64-bit Internet Explorer, so we need to leak the address of some object, of some interesting object. After the leak, we are able to make any kinds of fake attributes. So we can achieve arbitrary read by making a fake attribute of uint pointer type. And then we can achieve arbitrary write by making a fake JavaScript int array. With the ability to read and write arbitrary memory, we can set our shellcode and bypass CFG, bypass CMET, finally get RCE, get remote code excused. Okay, let's go through each step in detail. First things first. Wow. First things first, you need to be able to control the date in the unnaturalized memory. Because this is an unnaturalized memory bug, we cannot set our date after this unnaturalized memory block is allocated. Instead, we should control our date before this object is allocated, which means we should set our date in previous allocation. First, we allocate a memory block, say B1, and fill it with the content we need. Then we free B1. Here, although B1 is freed, but the content of B1 still remains because of the implementation. And next, we take our bug, and the uninitialized memory block, say B2 will be allocated. And here we let B2 just be allocated in the memory that freed by B1. This time, when we access to the uninitialized memory in B2, actually we are accessing to the date left by B1, which is controlled by us. Yeah. Here are some key points to successfully control the uninitialized memory. First one, which is obviously B1 and B2 should be allocated in the same heap. And the second one, the content of B1 should not be cleared after B1 is freed. This is dependent on the code implementation. For example, if B1 is freed by calling function memory protect free, then the content of B1 will be set to 0 after B1 is freed, and our control will be full. Last one, the content of B2 should not be set to 0 when B2 is allocated. This is also dependent on the code implementation. For example, if B2 is allocated with cmalloc, or using function heap lock, and with heap 0 memory flag set, then our control will be full. Fortunately, our uninitialized memory bug is controlled because the attribute array is located by calling function heap locate, but without this flag set, without the heap 0 memory flag set. So we are lucky. So we can control the date in C attribute value. I mean, the uninitialized C attribute value, we can control it. The next question is, what date should we use to fill in this C attribute value? Our plan is to set the VT type to a pointer type, such as string or object. So we need to set the value field point to a veiled memory address. If we are exploiting a 32-bit Internet Explorer, it would be simple, because we could spray a lot of memory block and then let the pointer point into the memory we sprayed, like this address. But in 64-bit IE, this kind of heap spray will not work, as we said before. In 32-bit process, you may use a heap spray of 200 megabits to control the memory date in a certain address. But in a 64-bit process, the memory address space is so large that you have to spray more than 50 gigabits to do this, to do the same things. And I think it is impossible. So we need an information leak first. If your bug is good enough, then you can directly leak the address of some interesting object. But this kind of bug is real. And if you don't have such a bug, there is another way. You may first leak the address of some object in the same heap, and then combine with some kind of heap feng shui. After this, you will be able to get the address of some object you are interested in. And this is also what we do to exploit our bug. We call it relative heap spree. To do the information leak, first we allocate some attribute array. And each attribute array contains 9 attributes, which is the same with the unnaturalized C attribute array. We set the first attribute to point to a string which has 30 bytes in memory. Then we free half of this array, half of this attribute array. And because of the implementation, the content of the freed attribute array will not be cleared, will not be set to 0. We hope to control the unnaturalized C attribute array with one of these freed attribute array. Next, we tag our bug, and the vulnerable C attribute array will be allocated. If we are lucky, it will use the freed memory in step 2. And so, and the first attribute, which is unnaturalized one, will be a string attribute. It is also left by the freed attribute array in step 2. So if we access to this unnaturalized attribute, we will get a string attribute. Of course, we can read out the content of this string. Step 4, we free this string and allocate a runtime stale object. Yeah, this runtime stale object. It has the same size with the freed string. Now, if we access to this unnaturalized attribute again, it still thinks this attribute is the string attribute, although this string is already freed and reused by the runtime stale attribute. So if we read out this unnaturalized attribute as a string, actually we leak the content of the runtime stale object. The first field in the runtime stale object is a pointer, point to the runtime stale attribute array. That means we can leak the address of this string. This is important. It is really important. Because we can set any attribute to a runtime stale object. Here we set more than 5,000 attributes to it. After this, the size of the runtime stale attribute array is very large. And then we allocate some JavaScript int array. This array will be allocated somewhere just after the runtime stale attribute array. In previous steps, we already leaked the address of the runtime stale attribute array. So by adding a certain offset to this leaked array, we will get the address of one of these int array. This is our information leak based on the relative heap spree. We have leaked the address of an int array now, so we can make any kinds of fake C attribute value. We can make any kinds of fake attributes. Next, to make a fake C attribute value, we need to tag our bug again, but a little different this time. This time we use a string to control the unnaturalized C attribute value. First, we allocate some strings, of course, with control date. Then we free them, and because of the implementation, we have talked about it before. The freed string is freed, but the date remains. Next, we take the bug, and the vulnerable attribute array will be allocated. It will use the memory of the free string. So the content of the vulnerable C attribute value will be controlled by the string date. This time, we set the VT type to VT variant and set the value field pointing to the leak JavaScript array. This is the fake variant that in our controlled JavaScript array. We can modify it. We have fully control of this fake variant date. Variant is a date struct that can hold various type of dates. So you can see some interesting types, such as int pointer, uint pointer, or object. Here we use the uint pointer as our target. We set the type of the fake variant to uint pointer type, and set the value field to an address where we want to read. Then we read the attribute out in JavaScript. It actually will read 4 bytes from the pointed address. And this means we can read arbitrary memory now. You can see here is our self-defined function, and by calling function get attribute to read out a string, and the call function pass int to change this string to an int type. Something more to say, because we are exploiting a 64-bit Internet Explorer, the address is 8-bit length. So here you can see the address low and the address high. Use this function, we can achieve arbitrary read. We can achieve arbitrary read. So we get the ability to read arbitrary memory. Next, we want to achieve arbitrary write to continue our exploit. Usually in IE, we can grab the length field of a JavaScript int array to achieve arbitrary write. But our bug is a little different. In previous steps, we already proved that we have make a fake uint pointer attribute. So why not just make a fake JavaScript int array attribute directly? It is possible for us to make fake variant that contain a JavaScript int array, just with a large size. To make this fake JavaScript array, we need to set the variant type to VT dispatch. So this time, the value field would be an object pointer. We let this pointer point into our leaked array, so we can fully control the object date. Next, we create a normal JavaScript int array, and then copy the content from this normal JavaScript array object to our fake JavaScript int array object. After this copy, our fake JavaScript int array object will have the same context with the real object, except that we set the length of this fake array object to a very large size. You can see here, the length field is very large. So, using this large size array, we can write and read arbitrary memory. Before executing our shellcode, we still need to bypass CFG and bypass CMET. Actually, this is not a big problem. if you have the ability to read and write arbitrary memory. Here we list some possible ways to bypass CFG, and some of them are already fixed, but some of them still not until today. For example, you can use the ability of read arbitrary memory to find the address of the stick. You find the address, and then you can rewrite or overwrite the return address of a function. After overwrite, when the function returns, the code flow will jump into your code. And the CFG checker will not check this value. Another example called Wild API. There are several APIs in the CFG whitelist. And what's more, it has the ability to indirectly or directly to change the EIP's value. For example, nt-continue of the function long jump. So using these kinds of functions, you can bypass CFG. Okay. After bypass CFG and EMET, we are able to execute arbitrary memory. Oh, sorry, we can execute arbitrary code now, but you can see it still runs in app container. And we have a demo here.
Okay, let's have a simple demo here. Is there anyone want to pop up a calculator in IE? No? Okay. Yeah. Okay, so we just start in the Net Explorer and visit our exploit address. Yeah, very quickly. And you can see this calculator, which is notable is here. You can see it still runs in app container. So our next task is to bypass the app container sandbox. Okay, enhanced protected mode is introduced in IE 11 in Windows 8.1, and it uses the mechanism called the app container to further restrict the rights of the sandboxed processes. It restricts their access to system resources. Basically, the processes running on the app container will have very limited access to system resources. For example, an IE sandbox process even has no rights to access the low integrity temp folder. So we use a bug called CV 2015 and 1743. This is a TOC-TOU bug, or sometimes known as a race condition bug. It is a logical bug instead of memory corruption bug. This bug exists in the IE install broker service. So let's introduce the broker service in Windows 8. As we introduced previously, the app container process have very limited access to system resources. But sometimes this process need to access certain resources to provide their normal functionality. For example, IE may need to install some plugins, and a Flash plugin may need to access a Flash folder to access their cache data, such as this. So there are some processes in the system running in medium integrity level. And this process provides the functionality to the app container processes to help them to access system resources. And IEAX install broker is one of these broker services. It is used by Internet Explorer to install add-ons or plugins. The process which provides this interface called ieinstall.exe, and it is running in media integrity level. This interface is accessible from within an app container process, which means if we achieve the remote code execution in app container process, we can just write code to access this interface. And we can use this interface to install plugins. Basically, to use this interface to install for example, an executable file, we need 3 steps called verify file, install file, and register exe file. We first acquire a interface to this broker, and we just call these 3 functions one by one. And if either of these functions fails, the installation will be failed. So let's have a look at what exactly these 3 steps do. First step is called verify file. This is the most important step from the perspective of security. It will try to verify that whether the file you are trying to install has valid signature. Your file must have a valid signature. Otherwise, the verify file step will be failed. And it also checks that the file you are trying to install is from a folder that which is not low integrity level. You will at least have this file under the medium integrity level folder. Otherwise, it will also fail. And the second step, called install file, it is just simply copy the file to our destination folder where you want to install this file. And the third step, which is also important, it will just call create process to execute the file you want to install. It seems okay because this interface will first try to verify that the file you want to install has valid signatures. But if you review the 3 steps, again, you may find there is a race condition problem here, which exists between step 1 and step 3. Because this file is verified in step 1 and executed in step 3. But before it executes this file in step 3, it does not verify this file again. Which means if you are able to replace this file between the step 1 and the step 3, then it will, the install broker will not know that the file is not the one that verified in the first step. And this is a bug. To exploit this bug, it is very straightforward. First, we call verify file to verify an valid file, which has valid signature. For example, we just verify the Internet Explorer executable, and of course this step can be parsed because this file has a valid signature from Microsoft. And second, we call install file, and the iExplorer executable will be copied to our destination folder. And here is the most important step. Before we call the third step, we just delete the Internet Explorer file and replace it with our own executable file. You can see we just replace a calculator named iExplorer.exe here, and then we call the third step register exe file, and and this file will our payload will be executed by the broker service, which means our payload can run in media integrity level, and we bypass the enhanced protect mode sandbox. Here's another problem here in order to use this exploit process. Since we need to be able to replace the file in the destination folder, it means we must have write access to this destination folder. So we must find a folder which we can write within the app container process. And basically this is, there's not many such folders since app containers has very limited access to system folders. So here, another broker service helped us, which is a Flash broker. Flash broker is used by Flash plugins, and it provided some interfaces to the Flash plugin to read and write some system folders. You can use this broker to read and write some predefined locations in the system, such as this one, the app data roaming Adobe folder under the user folder. And you can use the broker to write into this folder, and which is important. This folder is not low integrated. So this is exactly the one we want to find. Another little problem here is Flash broker try to prevent you from writing the dangerous file, for example, executable files, to its folder. So there is a whitelist that of the file extensions that you can write to use this broker. And the exe file is not in this whitelist. But that's not a big problem, because the create process API will just will check the actual file type. So even you name your file as one.jpg and call create process on it, it can still execute it as a valid PE file. Yeah. So this whitelist is just useless. Okay. There's the last defense line of Flash broker to try to preventing you from writing PE files to the folder. It will, when you call the broker function called the broker write file to write data to the file, it will try to check that whether you are writing a PE file by searching the PE signature. For example, the DOS head and the PE head here. And if it finds such signature, it will consider that you are trying to write a dangerous file, and the write will be failed. But this check is not very useful, since it only checks the first time that you are trying to write to the file. So we can just bypass this check like this. First, we write the file data without the DOS signature. We just put a 0 in the location, and then we can call another function called broker set fire pointer, which is the same as the set fire pointer function in Windows API. So we can set the fire pointer back to the beginning of the fire, and this time we just write the DOS header, just write the 2 bytes DOS signature, and then we have a completed PE fire and bypasses its defense. So we have another demo here. So first we start in Internet Explorer, and you can see what? You can see the child process runs in app container, and now the PID of this process is a 2944. So we just inject our DL to bypass the EPM. To let you see the steps clearly, we have some message box in the DL, and you can see before we call install file, we can check the flash folder. You can see there are no extra files in here, and we will call install file to install the iExplorer executable first. And you can see it is installed. Here we have the file named test.bin.temp. And actually it is Internet Explorer executable. And it has a valid Microsoft signature, which helps us to bypass the first check. And then we will overwrite this executable with our own payload. And you can see, after we overwrite this file, the file size becomes small, and actually it is now our payload executable. And then we just call the last step, and you can see our executable is executed by the iInstall broker service here. This test one bin, and you can see this process already runs in media integrity level, which means we have bypassed the EPM of Internet Explorer, and that's go back. And this time we have fully succeeded in this target. We want to thank Black Hat Committee to have us here, and thanks to Zero Day Initiative to have the Pontoon contest. And also we want to thank the guys in 360 Volt Can team and for working this exploit together. And so this is the key point of our our talk today, and we introduced some technicals to exploit the latest Internet Explorer 11 for the 64 bits, and we introduced some method to exploit uninitialized memory bugs. And we also introduced how to bypass the EPM sandbox of Internet Explorer. Okay, that's all for our talk today. Thank you for coming, and if you have any questions, we will be glad to answer you. Thank you.